Okay, so this is a talk about async directory operations in Ceph, which is some work I started maybe roughly a year ago to try to speed up some particular workloads. But first of all, I'm Jeff Layton. I've been doing kernel development for many years now, and recently did a lot of work in NFS and CEPHES, and now I'm recently took over as the CephFS, CephFS maintainer upstream. And then I'll let Patrick introduce himself.
Hi, I'm Patrick Donnelly. I'm the CephFS team lead, been with Red Hat since about 2016.
Cool. Too many. Okay, yeah. So anyway, the real impetus behind this work is that I do a lot of work in network file systems, and doing directory operations over network file systems is typically really, really slow. I mean, you almost always have a synchronous round trip to the server. It's probably not surprising to anyone in this room, but this affects a whole lot of common workloads. I mean, untarring files, you got to do a lot of creates, and that means a lot of round trips when you're blocked and waiting for them to come back all the time. RSync, removing directories recursively, even building software, all that kind of stuff is really affected by metadata. Any metadata-heavy workload is going to be affected by this. So the first question is, why are local file systems so fast, right? And the obvious thing is that there's the connection between them and the backing store is pretty small, and so there's no round-trip latency to a server in most cases with a local file system. But also, turns out local file systems cheat. They typically will just journal they don't journal the thing, but they just do the operation in memory first and then go ahead and return back to user land, and then they'll, flush it out to the journal eventually, and eventually out to the, play back the journal out to the disk or whatever later. So that allows them to, batch up stuff to the journal, which is kind of handy. But also the ramification there is that if you do a create and then it succeeds, and then the box crashes like almost immediately after, that create basically didn't happen, right? There's a period of time where the operation occurs, and then it's not actually on any sort of stable storage, even though you've returned back to user land and the program is none the wiser. So now I'll step back for a minute, and I'm not going to go into heavy detail on this because Sam just did a bunch of it. But basically, CephFS is a file system that is based on top of Ceph, or top of RADOS. So Ceph is basically the core of Ceph is the RADOS, which is the sort of a distributed object store, and then we have a file system that sits on top. And the key point is that we have these MDSs up here, which act very much like a traditional file server, much like NFS or SMB server, something like that. Essentially, they just handle all the metadata operations. You want to do a create, you want to do an unlink, anything like that. That's where you have to go talk to the MDS, and it handles that and then returns a reply. Anything else you wanted to say about it, or did I miss anything?
Yeah, I just would emphasize, that in CephFS we did, at the time, fairly novel technique or architectural choice was that the client has direct access to the object storage devices for reads and writes. But still, as with most distributed file systems, we're dealing with this issue of the metadata traffic adding to the latency. While that's typically viewed as unavoidable, we're trying to find approaches to avoid that in this work.
So yeah, effectively yes. The clients in particular write directly to the the OSDs whenever they do or reads or writes. They do directly to the OSDs, much like PNFS. This is sort of a precursor to PNFS actually. So how does Ceph do this? How does it mediate the operations? Right. Well, it has this sort of novel mechanism called capabilities, and these are essentially revocable locks. Much like a delegation or an op lock in SMB or delegation in NFS. These are very similar kind of thing, but the main difference is that they are much more granular than is typical. So whereas usually when you get a delegation or an op lock with something like SMB or NFS, you get access to the whole file. Ceph does it a little differently. It breaks these up in different pieces. There is pin, which basically pins the thing to a particular MDS. There's auth, which covers UID, GID, mode. There is file, which covers a whole bunch of stuff. I'll go into that later. Link is the link count, basically, and then you have the XADDR capability, which is for XADDRs. No, all these capabilities pretty much have a shared exclusive variety, right? The MDS can hand out exclusive access for any of these capabilities to a client, and then if anybody, or it can hand out multiple shared ones to multiple clients, but not both. But file caps are a little bit special. They have because the way Ceph is done, and all the I/O is driven through directly to the OSDs. It has to mediate that somehow, and it does that through capabilities too. So clients are granted read and write capabilities, and that sort of gives them access to know what the file layout will be, for instance, but also mediates, when the client or when the MDS hands out like a write capability, it knows that there's a good chance that the client may be actively writing to the file. And then we have cache and buffer too. So you can either cache. Those allow you to cache the data that comes in off the OSD, or to buffer it for writes as well. So otherwise, you end up with more like a direct I/O kind of pattern, or where you are flushing direct, not through the page cache. And then we have, so we use this sort of shorthand notation when we discuss caps, usually because it's kind of complicated. So we have, this sort of string here that when you want to print out like what clients what caps does this client have, you can print out a string that looks something like that to show which cap bits it's holding. And down here, this is just a picture of when we track capabilities internally in the kernel or in userland too. It's done as a mask, like a bit mask, and so we track them. Each bit, each of these represents a bit in the bit mask, and then so you can say what capabilities you have by looking at the mask. So the idea here is that we want to extend file capabilities, which are largely unused on directories, and we want to extend those to use to allow asynchronous directory operations. So we want to be able to allow the client to do a create or an unlink or something like that, or rename potentially, and then do that and without having to necessarily talk directly to the MDS and get the reply. Because we are pretty certain when we have exclusive caps on a directory that we're the only entity in there and operating on it, we can be pretty sure that that operation will succeed most of the time. And so if we if we do that, then there's really no reason for us to have to stick around to wait around for a reply on a lot of these operations, right? We can just issue the thing and assume it's going to work, and then we will just if it doesn't, then we have to clean up the mess later. But in almost all cases, it will work. So internally in the MDS, we do this via a new lock caching facility. So Zhang is our lead on the MDS work, and he added a new facility. Typically, when you go to do like a create or an unlink or something in there, the MDS has to gather a set of locks so that you can do that operation to ensure that other MDSs don't interfere. And so what happens, and so what he's created is this new facility that allows us to gather these locks for an initial unlink or create in a directory, and then hold on to them, if there's no contention for them. So typically we do we gather up all these locks and cache them in the response to an initial synchronous create or unlink. So we have to do a first synchronous call in any of these to establish the lock cache. The other part is that when we're doing any sort of operation in a directory, we have to be able to ensure that we have cache, that we know what the state of all the entries in that directory are, or at least the important ones. And so Ceph has long had a mechanism for caching entry information. And so it can either hand out a positive or negative entry lease, so it has a mechanism for that. But it can also give out shared caps or exclusive caps on a directory. And so for that, if we have shared caps on the directory and we have directory completeness, if we know that we have we know about all the entries in that directory, then we can be pretty assured that we're safe to do this operation. And in fact, completeness is kind of handy too if we have shared caps, because we can do things like satisfy negative lookups in the directory without even talking to the MDS. So now we can talk about actually doing these things asynchronously, but first let's talk about what it looks like when you do a synchronous one, right? So, typically when we do a synchronous unlink, or we do an unlink in Ceph today, it's all done synchronously, right? You issue a call to the server, and I should mention that we started with unlink just because it's easier. Creates are quite a bit more difficult, and I'll go into why that is later. But the CephFS will, typically will issue a call to the MDS, wait for the reply, and then it returns to user land after the unlink is done. And this is particularly slow if you're like removing a big directory, right? If you've got a bunch of files in a directory, what does rm-rf do? It goes and does a redir in the directory first, and then it walks down all of those and unlinks all those files, and then finally removes the directory at the end. Each of those represents a round trip. So here's a diagram that kind of gives you an overview of how this works on today. But you can see here we have we're doing an open here, and it's going to fetch attributes and whatnot, blah blah blah. So we do all this stuff. We do a redir here. We get caps for the directory. We got exclusive caps, or this shows exclusive caps, but it doesn't have to be. And then we start issuing unlinks. And so this first one goes, it's synchronous. The next one goes, next goes, and then eventually at the bottom we get to go do an rmdir.
Jeff?
Oh, sure.
If the user if arguments R came in multi-threaded, would you do this sequentially as well? So
Well, rm-r is not multi-threaded today.
Yes, but
In principle, it could be. And would we do it would we still do it this way today? I mean, we'll look differently. I mean, of course, right? It would look. I should say that our goal here is to also improve existing workloads, right? We could certainly go rewrite all these tools to go and use to be threaded or something, and then that would change how all this looks, right? But but everybody uses single-threaded tar and single-threaded RM today, and so we want to improve that as well. So one of the questions we have to answer though is whenever we are going to issue one of these, so we want to do these asynchronously, right? But the question is, should we wait to buffer a bunch of these up and send them all out at once, or is it better to just go ahead and shovel them out as soon as we know we're going to be doing an unlink or a create? So whenever you consider this, you have to think about it's natural to think of like write back. If you're writing back data after a buffered write, it's a little different, right? With a buffered write, data is stored in the cage cache, and then we later write it back, of course, right? But we have it's always a high probability that that the same data will be modified or changed again in the future. So it's often beneficial with write back to just wait a little bit before you go and instead of aggressively trying to flush out writes. Directories are different though. Workloads that create and unlink the same files are pretty rare. And while we could try to improve those, I don't think it's probably worthwhile. So given that, we've decided, at least in the initial pass, to just shovel the calls out the door as quickly as we can, right? We want to, as soon as we know we're going to do an unlink, we just fire it off, and then we just don't wait on the reply. And we might change this in the future. There are some workloads that could benefit from waiting to do that. So for an asynchronous unlink, we have to have a certain set of criteria has to be met, right? We have to have, we have to have exclusive and unlinked caps on the directory. And again, we've overloaded the file caps for this because they aren't used for directories typically. We have to have a known positive entry. You can't go and unlink the thing and then find out later on it didn't actually exist. And then we have to have, and it also has to be what's called a primary entry. Ceph has a sort of odd way of tracking entries internally, that the primary entry is tracked in with is stored in with the INODE, And so because of that, it's really difficult to do this on hard link files. So we've kind of knocked them out for now. So yeah, and basically all we do is we just fire off the unlink call to the MDS, and then we immediately delete the entry locally. And when the reply comes in, we do a little bit of minimal processing to make sure, error handling or whatnot, make sure that we didn't get an error or anything. And then, but this allows, allows us to return very quickly from an unlink. So the catch here is that, because we are because we're not buffering these up in any fashion, right? An RMDIR has to wait for all the children to be unlinked before it can proceed. So, eventually we may try to support async RMDIR, but it's actually pretty hard to do that because of the way the dependencies between the different entries. Okay, and here's our graph again with a slightly different situation. Again, you can see here, right, the unlinks look a lot different, right? We're just firing them off as quickly as we can, and then eventually all the replies come back, and then eventually we can do the RMDIR. So performance, these are really rough numbers. I mean, I just kind of slapped this together on my personal home test rig. But if you, and here we're just removing all the files in a directory. I'm not actually removing the directory itself. So without async drops on this box, it was 10,000 files. It took about 10 seconds. But with them, less than a second. The catch, though, is that when you go to do if you did an RMDIR immediately after, that RMDIR will block with async drops. It turns out that it's still a little bit faster, just because we're effectively parallelizing all the unlinks, but but there is still significant delay when you go to do the RMDIR. And again, we'll also block too if you fsync the directory, we'll block and wait until all the unlinks are done. Some BPF graphs. These are histograms from BPF. I shaved off the actual bars at the end, so you can't, because they didn't fit on the slide. But if you see without async drops, these are all in nanoseconds too, by the way. So without async drops, they're all pretty slow, right? Between 512,000 and a million nanoseconds. You even have some much higher outliers there. But with async drops, a lot of them are down here in the thousands of nanoseconds, right? Which is pretty good. And then, eventually, I think we get this one down here too that is effectively this is the synchronous one, right? Most likely, or could be any of these actually. But occasionally we get some that are, where we get some that end up being slower. I need to do a little bit more performance work to go and look and see why exactly that is. But I think it's, we hit other bottlenecks, maybe in the transport. So we have some opportunities to improve this, right? RMDIR, again, has to kind of do an implicit fsync ahead of time. So, if you do, rm-rf on that test drops, right, it's going to behave a little bit differently. We probably need to do some tuning, right? We need to find the proper balance between, to throttle these things out, because you can really shove a whole lot of them out the door, quickly, and I think that can tend to overwhelm the MDS. And then we can also consider in the future batching these up. So we may want to change our approach and back off maybe, and wait and consider maybe adding batched unlink operations to the MDS so that we can shovel out dozens of them at a time. Now creates. Again, we have you need exclusive caps again on the directory again, and we need directory create caps, DC caps. We also need a known negative entry in this case, right? Because we're actually doing a create. So we need either DS. Either need. Well, we have directory shared by virtue of the fact that we have an exclusive cap, but we also need completeness, or we need a cached entry. And we also need a file layout. So when one of the things is that because all the I/O is done directly to the OSDs, the clients need to know where to write that data. So we need a file layout. And to do that, we usually copy it from the first synchronous create in the directory. And we also need a delegated INODE number. That's the one thing that, so we have to, and I'll talk about how we implemented that in a minute. So quite a bit more requirements for a create. So again, we fire off the create call immediately. We set up a new INODE, link it into the entry, and then return from open. So we assume that the newly created INODE, so usually whenever you create an INODE, whenever you ask the MDS to create an INODE, it usually will hand you back a full set of caps anyway, because it sort of assumes that you're the exclusive user of the thing. No one's seen this thing before. So it might as well give you all the caps for it. So we just kind of assume that that will happen here as well. And then we always set O exclusive on the call to the MDS, because there's no reason you shouldn't. If it turns out that the file did actually exist, we probably would want it to return an error and let us know rather than just soldiering on. So again, we need to know in advance, before we can return, we need to know what the INODE number is going to be, because we have to be able to hash the thing internally. We need to be able to allow, and also whenever you do a write in Ceph, the backing objects are stored with a name that looks like INODE number dot chunk number. And so if you don't know what the INODE number is, you can't know what the object names will be to write to. So we have to know that. So the MDS will now, new in Octopus, which is the latest coming Ceph release, it's going to hand out, the MDS will hand out a range of INODE numbers to the clients in create responses. So we have a new userland tunable, for the MDS, actually, to sort of tell how many it should delegate at a time. And so these are all, but these are not handled the same way as file caps are. These are tied to the MDS session, so if the MDS session is reconnected, then the client should, the client will resend the async creates with previously delegated inodes. This have work in progress here, but it's not really now. This actually does work. So the way this is handled, so the reason it was done this way is that typically when the MDS does operations, it will buffer, it will buffer them up and then, or journal them. And so by doing it this way, we can avoid journaling some of this information. Create performance is a pretty simple shell script here that I'm creating 10,000 files this time. So without async drops, I get, it's about 11 seconds to do this on this test rig. And with them, about half that. So not a bad improvement. So here's, again, histogram, time spent inside Ceph Atomic Open. So whenever you do a create in the, or whenever you do an open OCreate in the kernel, it typically will go through what's called an atomic open. So just that's the way that it's implemented internally. Again, without async drops, we have a lot of them that are pretty slow in this, 500,000 to 1 million range, most of them. But here, much faster, right? We see a whole bunch of these. Now we do have some outliers, right? There's a few of these down here that are really big. And so I think some of these, what happens is, again, I need to go in and do more analysis, but I think what happens is that we get to situations where we run out of inode numbers. So we end up, we're doing a bunch of async creates so fast, and then, the MDS hasn't had a chance to refill our pile of inode numbers, and then eventually we end up having to flip back to synchronous IO for a bit, or synchronous creates for a bit. And then eventually they resolve themselves. So it probably can improve that some. All-important kernel build test. So this is, I'm just have it, grabbed a random tarball, making a directory, CD into it, untar the thing, and then make the thing. So without async drops, took just under 5 minutes on this box. But with them, we shaved about 50 seconds off. So I think a lot of that is in the untar, but some of it is probably also in actually creating files to, for compilation. So again, we have opportunities to improve this here. One of the things we'd like to do is improve the rsync workload. One thing rsync does is it usually will create a file, and then rename it into place. So that means we still have to do round trips to the server for all that with this workload or with this patch set, but we can probably improve that if we were to buffer the rename. We could also batch creates, possibly, and then there's other operations we could do, make dir, symlink, whatnot. And there's always an opportunity to improve error handling, which is kind of the Achilles heel for this whole thing, right? So if we return early, right, from an unlink or create, right, what do we do when this fails? And right now the answers are not real great, right? So for creates, we may even have opened the file, written to it, closed it, and then all of a sudden we get a reply back from the MDS saying, nope, that create didn't work for whatever reason, right? And so we don't really have a great way to report that sort of error to the user right now. So actually I have some, and so when I started this work, I kind of hinged a lot of this on this fsync, this blurb from the fsync man page, which basically says, calling fsync does not necessarily ensure that the entry in the directory containing the file has also reached disk. For that, an explicit fsync on the file descriptor for the directory is also needed. So technically, we're within our rights to do this if we take this as being gospel, but it's not really great. So, but no, most people, not many people actually do sync, do that fsync on the directory. A lot of workloads don't, and in most cases, usually local file systems in particular are pretty fast about getting it to the journal. So it's not noticed that they're cheating. So what we do right now after failed unlink, we mark the directory non-complete, right, because we don't know what's in it anymore. We invalidate the entry, and then we set the write back error on the parent directory to show that, so that if you do that fsync on the directory, you do get an error. And after a failed create, we do very similar. We invalidate the entry, set write back error, and then we also set a write back error on the created inode too, so that if you fsync that inode and it's still open, you will get an error, but that's sort of a big if. I've got a patch set in progress. I'm trying, or a couple patches, trying to get in to make CephFS return errors properly. Right now, it doesn't really do that in the kernel in Linux. So that would be nice to have that working more properly. And I said here we may need to consider new interfaces, but I noticed that IOUring actually has create support now, so that may be something we could consider too. We might could do this with wire this into IOUring to be able to do this and handle it a little bit more sanely. And that's all I got. Anybody have questions? Okay, great. Thanks.